In the last lecture, we discussed about a probabilistic implementation for numerical integration. In this lecture, we can see some probabilistic implementations for a binary counter. We shall see how a probabilistic method helps us to increase the counting capacity of a binary counter. The topic for today is probabilistic counting. What are the basic operations in a counter? The first operation is initialization. If C is the counter variable, init will initialize that counter to 0. Then tick is a function which increments the counter value, which is the name given in the textbook. You can call it increment, but this is what the name we are using. Tick means increment. It represents a clock tick, that is why the name is tick. When a clock tick comes, it increments. Then the third function is count, which returns the present count value. For example, suppose you initialize a counter and after 10 clock ticks, if you call count, you need to get 10 as the counter value. That's it. That is, it should return the number of times the tick is called on the counter after the initialization. So only three operations: initialization, increment, and function to return the counter value, and the operations are named init to initialize, tick to increment, and count to return the count value. How far we can count using an n-bit binary counter? How many different objects can be counted using an n-bit counter? If it is a 2-bit counter, you can count from 00 to 11, only 4. For an n-bit counter, it is 2 to the power n. That is the number of different binary strings possible with n bits. A deterministic algorithm should increment the counter by 1 each time when the function tick is called. If the counter value is 9, then when it is called, it should increment it to 10. And when the function count is called, it should return, the deterministic algorithm should return the number of times tick is called after the last call to init. And here we allow the user to do initialization anytime, and that is why the value returned should be the number of times tick or increment happened after the latest initialization. Naturally, a deterministic algorithm can go from 0 to the maximum value, which is 2 to the power n minus 1. When n is 2, 2 to the power 2, which is 4 minus 1, which is 3 is represented as 1, 1. So it's very clear that this counter cannot count beyond 2 to the power n objects or events. The maximum 2 to the power n events. The question is, can we go farther? Can we count more number of events using n bits? What do you think? Using n bits, it is not possible if you look at only deterministic implementations, but it is possible if you go for probabilistic implementation of the counter. Now we can look at a basic probabilistic implementation, and what it can do is, for implementing the tick function in a deterministic case, without any condition checking, the count will be incremented and function will return. But here what you do is you flip a fair coin, and only if the heads come you increment, otherwise you don't increment. So this is the implementation. Recall that coin flip is a basic probabilistic procedure that we discussed. It will return either yes or no uniformly at random. Sorry, heads or tail uniformly at random. If it shows a heads, increment, otherwise don't increment. You can easily see that if you call tick C say 4 times, what is the probability of incrementing? Every time it is 1 by 2 to the power 4, because 1/2 is the probability of an increment. So probability of 4 increments is 1 by 2 to the power 4, and probability of n increments is 1 by 2 to the power n. And when the function count is called, the implementation wants you to return twice the number in C. You note that you are not incrementing C always. You are flipping a coin, only if you get heads you are incrementing. And this algorithm is returning twice the present value in the counter. This is a particular implementation. So from this you can see that the counter stores an estimate which is expected to be 1/2 the number of times increment or tick is called after the last call to the initialization. It assumes that once in every 2 calls it is making an increment. That is a fair assumption, because we assume that it is a fair coin. So if it shows a heads now, maybe it shows a tails later in the next round. That is just an assumption, it may not happen, but you can prove that the expected value is 1/2. And now see what you are returning, twice the value represented as C. So what is the maximum possible value of C with n bits? 2 to the power n minus 1. Okay, and hence you can count twice the number of events, because when you have a 4-bit counter using a deterministic implementation, you can go from 0 to 15, 0 0 0 0 to 1 1 1 1. But here you are incrementing once only in 2 calls, once in 2 calls. That is the expectation. So when the count value is 1 1 1 1, which is 15, what you are returning is 30 30, and that is what I say, it is almost twice the number of events that you can count with a deterministic counter. And we can prove that the expected value of the count returned by the function, that is, this is what is returned, is exactly the number of tick functions called after the last call to the initialization, which is not the actual value. Actual value may not be the precise value of the count, but the expected value, this is a random experiment, and I think you know the basis of probability theory. So we are talking about the expected value of the count. You can prove that it is exactly the number of times you incremented the counter after the initialization. So this is a specific implementation, and when you are calling a tick, you flip a coin, and only if heads come you increment, otherwise don't increment. And when you want to return the count, you increment 2 into whatever be the present value, and it can be proved that what is it returning, the expected value of what it returns is actually the number of increments happened. So the probabilistic approach that we just discussed can count up to these many events. Why? Because the maximum value possible with n bit is 2 to the power n minus 1, and now you are returning twice that maximum value. What is it? 2 into 2 to the power n, which is 2 to the power n minus 1 minus 2. That's what I am telling. So the twice the events it can count. But that is not so interesting, because even though it allows to count twice the number of objects, you are getting an algorithm which is not always correct, which is a probabilistic algorithm. The expected value is correct, but the actual value at a point of time can be wrong. But only you are going up to twice the number of events, which you can do if you just allow one more bit in the counter. If you allow one more bit, you can count from 0 to n plus 1 bits are there, these many values, which is actually the number of events that you are counting is one more than what you can do with a probabilistic n bit counter. So an n plus 1 bit counter can provide that freedom. So when compared to the precision that you are losing, you can go for an n plus 1 bit counter. Now an interesting question is, can we go farther than twice the number of events using a probabilistic approach? We have seen one probabilistic approach with an n bit counter, which allows you to count as many as twice the number of elements that you can count with a deterministic algorithm. Then we said no, that is not enough, because that you can do with one more bit. Then maybe that is what you should do. You don't go for a probabilistic method, because it may give you imprecise value at some point of time. So don't go for that naive probabilistic implementation. You go for an n plus 1 counter, which is deterministic. Now we are asking this question, can we go farther? Can we increase the capacity of the counter, n bit counter, beyond twice the capacity of the deterministic case? The answer is yes, you can. In fact, we can go exponentially farther. We will see an example. Exponential probabilistic counter using n bits. And previously in the first approach, what we did, we managed the counter to store one half the actual value, one half. If t is the actual value, t is the number of times a tick is called, we store t by 2 in the previous approach. Now we are going to store base 2 logarithm of the value t. This is what we are telling. In the deterministic case, if t increments happened, c will store the value t itself. The counter value will be t, which is actually the number of times tick is called. In the first probabilistic approach, we store t by 2. Now we are going to store log t to the base 2. Okay. Now what you return? In the previous approach, when you stored t by 2, you return 2 into t. Now you are asked to return 2 to the power c minus 1. You return that. We can prove that probabilistically it is correct, because the expected value can be correct. But for that we may need to do one more increment, because actually you have to do, or you have to return 2 to the power c, because c is actually log t. So the actual value you should return is 2 to the power c, but you are returning a number 1 less than that. Later I will tell you why the algorithm is doing that. Now suppose we count before you increment the value of the counter. So what is the actual value? It is the initialized value 0. And before you increment, it is only the initialized value. So C is 0. So what you are returning is 2 to the power 0, which is 1 minus 1, 0. So in that case, you are returning the precise value. It makes sense to return this, at least for the initialized case. Now the question is, then what should be the implementation for tick when you wanted to store log t in C? We can look at a given implementation. What is it doing? If C is the present value, from 1 to C you flip a coin, and if you are getting heads in the first coin flip, you return without incrementing and you repeat. So it will increment only if you get tails every time when you flip the coin. So the probability is 1 divided by 2 to the power C. The probability of increment is that. So you can see that the counter C stores an estimate of the base 2 logarithm of the actual number of times the tick or increment is called after the initialization. Now you can easily see that this implementation can count from 0 to this quantity. Why is it so? Because what you are returning, if you go back and see what you are returning, 2 to the power small c minus 1. So what is the maximum value which can be returned? The maximum value of small c, which is an n-bit binary value. So what is the maximum n-bit binary value? This is the maximum n-bit binary value, 2 to the power n minus 1. So this is the maximum value which can be returned by the count function in the second probabilistic implementation. And you can see that if you substitute the value of n, the number of bits, as 8, the second implementation can count more than 5 into 10 to the power 76 events, such big quantity. And the estimate of the number of times tick is called after the last initialization is 2 to the power c minus 1. That is what we saw. What count is returning is if c is the present value, which is log t, 2 to the power c minus 1 is what it is returning. But you know that because it is log t, to be correct, what you have to return is 2 to the power c, but not 2 to the power c minus 1. And for that, what you can do is you increment this quantity 2 to the power c minus 1. If you do an additional increment, then you will get 2 to the power c, which is the value that you can return or that you wanted to return. And that is possible only if we can do an additional increment. Now the question is, can we implement an additional increment? What do you think? Can you go for an additional increment in the counter C? The answer is no. In general, you cannot, because the maximum representable value for C is 2 to the power n minus 1, where n is the number of bits used to represent C. Okay, that is the maximum value. If you already reached the maximum value for C, you cannot go for an additional increment. That is the general answer. But suppose we allow the additional increment. If you allow that, definitely the system will crash due to overflow if you increment the maximum value. But assume that the probability of that error is very small. Recall from the lecture L48 that in a probabilistic algorithm, it is not prohibitive to allow situations like overflow, division by zero, because this is probabilistic, and if the probability of occurrence of such an error case is very low, you can allow. Suppose we allow that. With a very small probability, say P, you allow an additional increment on C. So what is the expected value which is returned? When you do that additional increment, what you are returning is 2 to the power the additionally incremented value. Originally it is C. If you go for an additional increment, it is C plus 1. And what is returned is 2 to the power the present value, which is the increment value, minus 1 with probability P, plus if P is not happening, that event is not happening, then the probability of the other is 1 minus P, that you all know. 1 minus P when you don't have an additional increment. So this is what you are returning. This is the expected value of the count when you allow that additional increment with a probability P. That is the probability P into what you are returning when you do the additional increment, plus 1 minus P into when you don't do what you return when you don't do the additional increment. If you solve it, if you multiply inside, this is the equation that you are getting. You can verify it offline. Then here you can cancel the minus P and plus P. You will get this equation. Now I am going to take out P multiplied by 2 power C from the first and last term. Now what is remaining in the first term is 2, and what is remaining in the second term is 1. 2 minus 1 plus this quantity. Now what is 2 minus 1 is 1. So this is what we are getting. The expected value of the count which is returned is this when you allow the additional increment with a probability P. Now we can see that when you substitute that small probability value P as 1 divided by 2 to the power C or 2 to the power minus C, when you substitute the probability P as 2 to the power minus C, which is a very small value, what is the expected value of the count returned? You substitute P as 2 to the power minus C in this equation. So what is it? The first term is 2 to the power minus C multiplied by 2 to the power C, which is 1. So it is 1 plus 2 to the power C minus 1, which is equal to 2 to the power C. This is exactly what you want to return, because what you are storing in C is log T to the base 2. So if you return 2 to the power C, which is the correct value. And not that with a very small probability we are allowing an overflow case. So we are allowing that with a very low probability value, and it is a very rare chance to get into the maximum value and then you go for the increment, and that is why you allow it. Now we have seen two different probabilistic implementation. One can count twice as many events as possible with the deterministic approach, and the second one can go exponentially more events in counting. Now what is the precision? You can see that the variance of the value of C after m number of increments is m into m minus 1 divided by 2. Again, from the basis of probability I am using variance. Variance is this, and the standard deviation is 70% when compared to the actual value of the required counter. The standard deviation of this implementation is, or what is returned by this implementation is 70% different than what you get. So it is not recommendable for a practical application. For instance, this probabilistic implementation, the second one, can distinguish 1 million from 1 billion, 10 to the power 6 and 10 to the power 9. But it cannot differentiate between 1 million and 2 millions. So it is not practically recommendable, but in any practical case with an 8-bit counter, we may not have to count as many as 5 multiplied by 10 to the power 76 events, which is what is possible with the method 2. So what we can do is, we can try to modify. We can significantly reduce the error probability if we let the counter store an estimate of the original value, which is base 1 plus epsilon logarithm. Previously it was base 2 logarithm. Rather than 2, you are going for 1 plus epsilon, where the value of epsilon is between 0 and 1, less than 1. Okay, we can look at that implementation which is given in the textbook. Let the counter store an estimate which is base 1 plus epsilon logarithm of the original value. This is what I am telling. Rather than storing t as such, store log t to the base 1 plus epsilon. And then what you can return is, this is what the algorithm is saying. This is the quantity that is going to be returned when you call the count C function, count on C. Now here again we can see that if you call the count just after initialization, before you do any increment, so the value of C is 0, what is 1 plus epsilon raised to 0? Is 1. So it is 1 minus 1 is 0 divided by epsilon is 0. So the count, the actual value is 0 and what you are getting is 0 from this implementation. That's okay. And by substituting the value of epsilon as 1/30, we can see that the new implementation allows you to count up to 1,25,000 events with an 8-bit counter, with 24% relative error 95% of time. So the precision is high. It is also allowing you to count a large number of objects, and maybe the precision is acceptable. So this is another one. With this we are finishing this lecture. Today we have seen some probabilistic implementation for a binary counter. We saw that the probabilistic implementation allows us to increase the counting capacity of an n-bit counter. The first implementation allows to count twice number of elements than the deterministic algorithm. And the second implementation is not so precise, but allows exponentially more number of objects to be counted. And finally we looked at a more reasonable and acceptable implementation which also extends the counting capacity but useful in practical applications. Thank you.